morning, students. So today I'm going to discuss the lateral load analysis of frames by Cantilever method. So in the previous video we have discussed total method of analysis, and I have mentioned that when the height to width ratio of the frame is moderate, we go for total method. But if the height of the columns or the height of the frame is comparatively larger when compared to the width, or height width ratio is large, the behavior of the columns is just like cantilever. So the cantilever action of the frame will be taken into account, and the cantilever method of analysis is used for lateral load analysis of frames for which the height width ratio is large. Today I am going to discuss the cantilever method of analysis using the same example which we have done in the previous video. Okay. Now coming to the cantilever method, this is also based on two different assumptions. The first assumption is the point of contraflexure of all the members is at the midpoint. So accordingly, this is the frame which I am going to do the analysis. A frame of 7 meter first span, 3.5 meter second beam, and 5 meter the third beam. And height of the stories, top story 3.5 and bottom story also 3.5 meter height. Two loads, 120 kilonewton and 180 kilonewton are acting at the nodal points A and E. So the first assumption is there is point of contraflexure at the midpoint of column and beams. This mark here. All the midpoints have marked the point of contraflexure. That's the first assumption. Second assumption is, in this case, we consider the area of cross section of columns. That is, axial stress in the columns is proportional to its distance from the centroidal axis of the frame. So, here the stress in each column varies according to its distance from the centroidal axis. So, for the first step is, we have to determine the centroidal axis of the columns or the centroidal axis of the frame. That is the first step. So, to find the centroidal axis, I have assumed, I have taken this left hinge column AEI as reference, and from this left, the centroidal axis is at a distance, say x bar. How to locate x bar? So, x bar is, we have studied in your first year engineering mechanics how to locate the center of gravity. A1 x1 plus A2 x2 plus A3 x3 plus A4 x4 divided by the total area A1 plus A2 plus A3 plus A4. Now let us assume all the columns are having the same area. So if the column AE is having area A, EA is also having area A. So totally the left edge column, the total area is 2A. 2A. I am taking the left edge AEI as reference. AEI as reference. So 2A is 0 plus 2A, the second column, that is located at a distance of 7 meter. Plus 2A into 10.5 plus 2A into 15.5 divided by all the columns together, the area is 80. So we will get 8.25 meter. So we have got the center of gravity of the frame is at a distance of 8.25 meter from the left edge. That is the first step. Okay. Now let's see the second step. To find the axial forces in columns. So for that, I am considering the top story columns. I have marked the column A up to the point of contraflexure. The first top story columns. And there is a load acting at this point A, 120 kilonewton. I mark the lateral shear or the horizontal shear in the columns H1, H2, H3, H4 at the point of contact pressure, and axial forces in the columns for the columns on the left side of the center of gravity axis. This is the CG axis. On the columns on the left side, or we call it as the windward side, or the side from which the load is acting, these columns are subjected to forces, tension. So I have marked V1 and V2, pull. The columns on the leeward side, that is on the right side of the center of gravity, they are subjected to axial thrust. So V3 and V4 are marked upwards, V1 and V2 are marked downwards. This we have got in the previous example also. Or when there is in a cantilever action, the columns on the side from which the load is acting, or the windward side, will be in axial tension, and the other two will be in axial compression. Now our aim is to determine the value V1, V2, V3, V4. That is the first step. So the second assumption we are going to make use of, that is axial stresses in columns are proportional to the distance from center of gravity. So I have marked here the first column. It is at a distance of 8.25 meters. So x1 is the same as x bar. Distance of the first column from CG. Distance of the second column from the center of gravity is 8.25 minus this 7, 1.25. The distance of the third column from the CG axis is 2.25. Distance of the last column from the CG is 7.25 meter. So the second assumption, stresses V1 by A. V1 is the force in the column, so V1 by A is the stress, divided by x1 equal to V2 by A divided by x2, V3 by A divided by x3 is equal to V4 by A divided by x4. The second assumption, stresses in columns are proportional to their distance from CG. Since all the areas are same, we can write V1 by x1, V2 by x2, V3 by x3 is equal to V4 by x4. Substituting this, we will get V1 by x1 8.25, V2 by x2 1.25, V3 by x3 2.25 is equal to V4 by x4 7.25. Okay, now we have to determine V1, V2, V3, V4. V2 equal to V1 into 1.25 by 8.25 0.1515 V1. Similarly, V3 is equal to V1 into 2.25 divided by 8.25 0.2727 V1. V4 is equal to V1 into 7.25 by 3.25 0.8788 V1. Then we have got the expression for V2, V3, V4 in terms of V1. Now, take moment of all the forces about the point of contact pressure of the right edge column, let it be M. So you take moment about point of contact pressure M, that on the right end of the column. So it is 120 into 1.75 a clockwise moment. 120 into 1.75 over this point. This V1 will be producing an anti-clockwise moment. So minus V1 into 15.5 minus V2 into 8.5. This V3 will produce a clockwise moment. So plus V3 into 5 is equal to 0. Now in this we substitute 120 into 1.75. For V1 we have V1 into 15.5. For V2 we have 0.1515 V1. For V3 we have 0.2727 V1. So from that we get V1 equals 13.615. V2 equals 0.1515 V1. 2.063 kilonewton downwards. V3 is equal to 0.2727 V1. Will work out to 3.713 upwards. And V4 is equal to 0.8788 V1. 11.965 upwards. Now, to get the axial forces in the bottom story columns, on similar procedure, let us assume on the bottom story the axial forces are V1 dash, V2 dash, V3 dash, V4 dash, and H1 dash, H2 dash, H3, H4 dash are the horizontal shear in the columns in the bottom story. I'll consider this point on the right column, say N, the point of contract rupture of the right hand column N of the bottom story. Take moments of all the forces about this point N. So taking moment about N, this 120 into 3.5 plus 1.75. 120 into 5.25 plus 180 into 1.75. These two produces clockwise moment. V1 dash into 15.5. V2 dash into 8.5 minus these two are anti-clockwise. V3 produces clockwise moment. So plus V3 dash into 5 is equal to 0. As earlier, substitute for V1 dash, V2 dash and V3 dash as V1 dash is 0.15, V2 dash is 0.1515 V1 dash, V3 dash is 0.2727 V1 dash, V4 dash is 0.8788 V1 dash. Substituting for V2 dash and V3 dash in this equation in terms of V1 dash, we get the answers. V1 dash is equal to 61.267 kilonewton downwards. V2 dash is 9.282 downwards. V3 dash 16.707 upwards, and V4 dash 53.842 upwards. So thus, under the first step, we have got the axial forces in both the top story columns and the bottom story columns. Okay, so from the first step, the answers which we have got for the top story columns, axial force 13.615, 2.063, 3.713, 11.961. From this, we have to arrive at the shear force in the beams. Considering the top beam, consider the beam AB. You consider the vertical equilibrium of this joint. Consider the 13.615 is acting downwards. So this force in this AB at this edge A will be 13.615 upwards. This point of contract friction, we mark the shear force at A. Shear force at A for beam AB. I am considering beam AB. Shear force at this edge A I am marking near to this because To make it clear, the shear force at this end is 13.615 kilonewton upwards. If so, the shear force at B, for the same beam, the shear force at B will be 13.615 downwards. Now coming to here, join B or beam BC, shear force at the edge B. There is a force, so this is 13.615. This is also 13.615. So I want to find out the shear force in beam BC at this edge. See, there is a load of 13.615 acting downwards here, and another force of 2.063 is acting downwards. So if you consider this joint equilibrium of joint B, I can write minus 13.615 acting downwards, 2.063 acting downward, plus the shear force in beam BC is equal to 0. So this is the vertical equilibrium of joint B. Minus 13.615 minus 2.063 plus shear force in BC equal to 0. This will give you the shear force BC is equal to 15.678. So at this end it is 15.678. If so, this should be 15.678 downward. Similarly, come to this joint C. Similarly, considering joint C, shear force in CD, in beam CD, this 15.678 is acting downwards, so minus 15.678. This 3.713 is acting upwards, so plus 3.713 plus shear force in beam CD equal to 0. So from that we get the shear force in beam CD is equal to 11.965 upwards. So this is 11.965. So this is 11.965. Let us check. You can check here. Join D 11.965 downwards and 11.965 upwards. So this join D is in equilibrium. Okay. So let's check. Sigma B is equal to 0 at join B. This is how we arrive at the shear forces in beams. So this is the shear force in chop beams. Now we have to come to the shear force in the bottom beams. So now coming to the shear force in bottom story beams. These are the bottom story beams. Columns, the axial forces, we have got these values from step 1. These are the axial forces in columns of the top story. Now coming to this beam EF. Coming to beam EF. Beam EF. Consider equilibrium of joint E at E. We can write 13.615 is acting upwards, 13.615, 61.267 downwards, minus 61.267, plus the shear force in EF is equal to 0. From that we get the shear force in EF is equal to 47.652. So this is 47.652. That is 13.615 plus 47.652. This will be equal to 61.267. Now coming to, if this is 47.652, on the other side this should be 47.652. Now coming to beam FG, consider beam FG. Considering joint F, 47.652 is acting downwards. 9.282 is acting downward. 2.063 is acting upward. Plus shear force in this beam FFG. Shear force in FFG is equal to 0. From that we get shear force in FG is equal to 54.871. So this value is 54.871. So we get this downwards 54.871. Now in beam GH, we consider beam GH or GH. What are the forces? 54.871 acting downwards. So minus 54.871, 3.713 acting downwards, plus 3 minus 3.713, 16.707 acting upwards, plus 16.707. Shear force in GH is equal to 0. From that we get shear force in GH is equal to 41.877. So this value is 41.877. So here it will be downwards 41.877. Let us check at joint edge. Check. Consider joint edge. 41.877 is acting downwards, so minus 41.877. 11.965 minus 11.965. This is 53.842 plus 53.842 is equal to 0. So the joint equilibrium. Thus we have got as the first step the axial forces in all the columns, top story and bottom story. Then the second step, based on the vertical equilibrium of each joint, we have arrived at the shear force in all the beams at both ends. Okay, now we have to find out the bending moment at the ends of the beams. Consider the top story beams ABCD. We have got the shear force values from the previous step, that is marked here. For the beam AB, the shear force is 13.615. So this is 13.615. This distance is 7.5 by 2. So the shear force at bending moment at A. Bending moment at A is equal to the shear force in the beam into L by 2, span by 2. So this is 31.615 acting at a distance of 7.5 by 2. So this into 3.75 will give you the bending moment at this. This is a clockwise moment this produces. So this is going in anti-clockwise direction. So to resist that, the bending moment at A of the beam should be equal to a clockwise moment. So bending moment at A for beam AB is equal to 13.615 into 7.5 by 2. It works out to 47.6 kilonewton meter clockwise. So this value is 47.6. If this is 47.6, at this end B also there should be the same moment clockwise 47.6. Now coming to this joint B, I have to find out the bending moment in beam BC. For beam BC, MBC will be the same as MCB, that is equal to the shear force 15.678 into 3.5 by 2. 15.678 into 3.5 by 2 will work out this moment, and that value is 27.4. So this bending moment is 27.4. This is clockwise. This will also be clockwise. 27.4 kilonewton meter. Now coming to this beam CD. MCD is the same as MDC. It's equal to 11.965. If the span is 5, so 5 by 2. It works out to 29.9. So this moment here is, both these moments are 29.9. 29.9 kilonewton meter. So thus we have got the bending moment at both the ends of the beams as shear force into span by 2. Similarly, we can arrive at the bending moment in beams at the bottom story. Coming to the bottom story beams, these are the shear force values we have got from the earlier step. So again, easily write the bending moment in this beam here will be 47.652 into 7.5 by 2. It will work out to 166.8. Shear force in beam FG at this end 54.87 into 3.5 by 2 will be 96. Shear force in GHS 41.87 into 5 by 2. So it goes on to 104.7. Okay, so from the first step, we have got the bending moment at both ends of the beam as shear force in the span by 2. Similarly, shear force in the span by 2. We have got all the bending moments in both ends of the beams. Okay, now we are passing on to the next step, bending moment in the column ends. What are the bending moment at the both ends of the column? So for that, I have marked the values obtained from the previous step, the bending moment in B, 47.6, 27.4, and 9.4 like this. Now considering this equilibrium of joint A, consider the moment equilibrium in this column. Column A, the moment at A will be, if this is 47.6 clockwise, this has to be 47.6 anti-clockwise. Since there is point of contact structure at the midpoint, at the column edge, at the edge E, the moment will be equal to same anti-clockwise 47.6. Now coming to this joint B, 47.6 clockwise here, 27.4 clockwise. You have moment equilibrium. This should be having an anti-clockwise moment in the column at the joint B. The value of moment in right here, moment MAE is the same as moment MEA. That will be equal to minus 47.6 anti-clockwise. Anti-clockwise. It is from joint equilibrium of A. Coming to joint B, 47.6 clockwise moment, 27.4 clockwise moment, plus momentum BF is equal to 0. From that we get MBF is equal to minus 75. That means this moment is 75 kN anti-clockwise. That will be the same here also. At this end it should be 75. Similarly, coming to joint C, 27.4 clockwise, 29.9 clockwise. So 27.4 plus 29.9 plus moment in column CG should be equal to 0. From that we will get moment in column CG is minus 57.3. So this column moment is 57.3. Coming to this, 29.9 clockwise, so it is anti-clockwise, 29.9. Both ends, the same value. In this end also, 29.9. So thus we have got the bending moment in both ends of all the columns of the top story, just by looking into the joint equilibrium. Now coming to the bottom story. Bottom story column EI. So there is 47.6 anti-clockwise, 166.8 clockwise. So what will be the bending moment in EI? We can write minus 47.6 plus 166.8 plus MEI. Bending moment EI is equal to 0. From that we get MEI is equal to minus 119.2. So this is anti-clockwise 119.2. So 119.2 plus 47.6 is 166.8. So this B moment and this column moment, these two columns moment plus this B moment should be equal to 0. This is 119.2 here. Here also which is 119.2. Now coming to joint F. Here 166.8 clockwise moment minus 76.75. 166.8 clockwise. Then from the beam there is 96 clockwise. And this column moment is minus 75 plus the moment in Fj. Repeat once again. 166.8 and 96 are the beam moments. Both are clockwise. This column moment at the top story is minus 75 plus MFJ equal to 0. From that you get bending moment in column FJ 187.8. So this will be 187.8. So this 187.8. Similarly at the joint G 96, 104.7 clockwise and 57.3 anti-clockwise. So I can write 96 plus 104.7 minus 57.3 plus mgk is equal to 0. From that we get mgk is equal to 143.4. So this is 143.4. This is also 143.4. Now coming to joint H, 104.7 clockwise, 29.9 anti-clockwise. So this will be 104 minus 29.9, 74.8. So 74.8. So we have got the bending moment at both the ends of all the columns by considering sigma m is equal to 0 at each joint. Okay, we have got the bending moment at both ends of the columns from the previous step, and that is marked with the figure 47.46, 75, etc. The last step is to find out the horizontal shear in the columns. So we know the bending moment M is equal to, if this H is the horizontal shear H1, which is equal to H1 or H into the column height H by 2. The moment in the column is equal to the horizontal force into this H by 2. This H by 2 is 1.75. If so, what will be H1? H1 will be equal to, which will be equal to QM divided by H. From that we can get the horizontal shear in column AE. The shear in column AE is equal to bending moment 47.6. That will be 2 QM divided by H. The total height of the column is 3.5. So bending moment or the shear force in column AE is 47.6 into 2 divided by the total height of the column is 3.5. So from this works out to 27.2 kilonewton. So this value is 27.2 kilonewton. Similarly, the shear force in column BF is 2M. M is 75. 2 into 75 by the column height 3.5. It works out to 42.85. So this we get as 42.85. Similarly, this will be 57.3 into 2 divided by column height will be 32.74. And moment in shear in DH will be 29.9 into 2 divided by 3.5, 17.08. Similarly, the shear force in the bottom story columns are 119.2 into 2 divided by 3.5. It will work out to 68.11. Shear will be 187.8 into 2 divided by 3.5. 107.31. Shear here will be 143.4 into 2 divided by 3.5. 81.94. And finally 74.8 into 2 divided by 3.5. 42.74. Thus, we come to the end of the analysis. So, in this method, the different steps involved were: first, we find out the axial forces in the column based on the assumption. From the axial forces, we find out the shear force in beams. From the shear force in beams, we get the bending moment in beams. Based on the bending moment in beams, by joint equilibrium, we get the column moments. From the column moments, we get the horizontal shear in columns. So, all these results, we have to express it in a pictorial way or in a tabular form way. So, I'll show you the final result in a graphical representation. Okay, so now we are going to graphically represent all the results which we have got after the analysis. The first figure shows the bending moment diagram for columns and beams. Let me first discuss the bending moment diagram of columns. The bending moment in column A was 47.6 anti-clockwise. So with this pointing in this direction, anti-clockwise direction, 47.6, it will come here. Here also 47.6, the pen pointing like this, anti-clockwise, 47.6, connect them. Similarly for the next column, 75, anti-clockwise, 75, anti-clockwise, connect it, you get the column diagram. Similarly, the bending moment diagram for all the columns is drawn with point moment 0 at the point of contraflexion. Next for the beam bending moment, the bending moment in the first beam AB, clockwise moment 47.6. So A to B you place the thumb pin like this, 47.6 clockwise. So 47.6 clockwise, it will reach here, this vertical line. Here also 47.6 clockwise. So B to A, place the pen like this, rotate clockwise. So 47.6 up, connect them. So that's 0 moment at the center. Similarly for the next beam, 27.4 clockwise, 27.4 clockwise, connect it. Similarly for all the beams, so we get the bending moment diagram for columns and beams. If you want, we can draw it separately in two figures. This is the combined figure in one diagram. Next we will see the axial forces in columns and shear force in beams and columns. So shear force in beam for the top beam 13.615, 15.678, 11.965. Similarly for the bottom story beams, mark the vertical shear forces. Then you mark the horizontal shear forces in columns 27.2, 42.85, 32.74, 17.08 for the top story. Similarly, mark it for the bottom story columns. Next, coming to the axial forces in columns. Axial force in the top story column, it is 13.615 tension, 2.063 tension. These two columns, 3.713 compression, 11.965 compression. Similarly, for the bottom story, 61.267 tension, 9.282 tension, 16.7 compression, 53.84 compression. Thus, we have completed the analysis of multi-storied building frames subjected to lateral loads by cantilever method, and all the results obtained from steps 1 to 6 has been represented graphically in two figures. Thank you.